Good evening, everyone, and welcome to tonight's NASA Connection. My name is John Mackin. I'm a NASA Solar System Ambassador. There are about 1,000 of us across the U.S., and as NASA volunteers, we bring news of NASA activities, discoveries, and missions to our local communities and schools. For upcoming events or to contact us for presentation, you can access our local Solar System Ambassadors webpage at ssa-si.com, which stands for Solar System Ambassadors Southern Illinois. You can also see previous presentations like the search for water on Mars or our Perseverance rover updates. You can check out some do-at-home activities and even get the latest NASA news. Tonight on the NASA Connection, we look at Cislunar Space and beyond, and look at how swarms of robots could help us explore our solar system and plan for future space missions. Thanks to both the St. Louis Academy of Science and to Dr. Jekan Thanga for their support of this event. Here's Rose Jansen with the Academy to share information about the Academy and introduce our presenter.
Thanks, John. I'm Rose Jansen. I'm with the Academy of Science St. Louis, as John said, and we're very pleased to be partnering with the Solar System Ambassadors of Southern Illinois to bring you tonight's NASA Connection seminar, Advancing Space Exploration Using Multi-Robot Systems and Swarms, and the Solar-Powered Lunar Ark Concept. For those of you who aren't familiar with the Academy, I'm going to take just a moment to tell you a little bit about who we are. We're an independent science organization supported entirely through community contributions. At venues throughout the region, we connect science in the community through free and or very low-cost public talks, science seminars and workshops, and trips and tours that feature scientists and engineering professionals of both national and international renown. In addition to advancing the public understanding of science, it's our mission to inspire the next generation of scientists and science advocates, which we do by offering a full array of free and low-cost opportunities expressly for teens, such as our Teen Science Cafes, STEM Teens Youth Leadership Council, Junior Academy of Science, and the Regional Academy of Science St. Louis Science Fair and its Honors Division. This year, they have all been virtual. The Junior Academy of Science is a pre-professional STEM membership organization for students from the full range of academic backgrounds in grades 6 through 12. It offers hands-on opportunities in science, engineering, and medicine. Teens can attend unique behind-the-scenes explorations of leading engineering, technology, and science labs of our region and participate in field opportunities and challenging and engaging science competitions. Currently, all of these are being offered virtually online, and Junior Academy members also make real-world connections needing top STEM professionals. You can find more information on the Junior Academy and all of our community-wide science events and programs by visiting our website at academyofsciencestl.org, or you may visit us on Facebook, Instagram, or Twitter. You can also sign up on our website to receive Academy e-news or jot your email address down in the online program survey, which will pop up in the chat a couple times this evening and during the Q&A before you leave. We ask that you take a few moments to fill this out. It lets us know how we're doing, what you thought about tonight's presentation, tells us what you thought about tonight's presentation, and helps us plan for the future. I do want to mention an upcoming event before I introduce our speaker this evening. On Thursday, July 8, also at 7 p.m. via Zoom, we invite you to join us for Would You Like a Nudge from a Robot? With Yun-Seong Song. He's Assistant Professor of Mechanical and Aerospace Engineering and Director of the Physical Human Robot Interaction Laboratory at Missouri University of Science and Technology. This event is free and open to the public, and you can register to attend on our website at academyofsciencestl.org events. I do encourage you to ask your questions as our speaker is presenting this evening. You can pop those in the chat window. However, everyone will be muted, so we won't be addressing those questions until the end of his presentation. And at that point in time, we'll go ahead and ask your questions of our speaker. So if you think of something you'd like to ask as he's speaking, feel free to jot that in the chat window. So with that said, I'd like to introduce the speaker this evening, Dr. Jekan Thanga. Dr. Thanga has a background in aerospace engineering from the University of Toronto. He worked on the Canadarm, Canadarm2, and the DARPA Orbital Express missions at MDA Space Missions. Dr. Thanga obtained his Ph.D. in space robotics at the University of Toronto Institute for Aerospace Studies and did his postdoctoral training at MIT's Field and Space Robotics Laboratory. He is an associate professor of aerospace and mechanical engineering at the University of Arizona, where he heads the Space and Terrestrial Robotics Exploration Laboratory and the NASA-funded Asteroid Center in Formation, Asteroid Science, Technology, and Exploration Research, organized by Inclusive E-Education, also at the University of Arizona. Jekan and his team of students have co-authored 150 technical publications, and Jekan is the engineering principal investigator on the AOSAT QSAT centrifuge mission. He and his team of students were winners of the Popular Mechanics Breakthrough Award in 2016 for proposing the SunCube femtosat, and recently won a Best Paper Presentation Award at AMOS 2019 for the early warning constellation to detect incoming meteor threats. We are pleased to have him here with us tonight in partnership with the Solar System Ambassadors of Southern Illinois for a look at space exploration using multi-system robots and swarm in service to sustaining human civilization. Won't you please join me with some virtual applause in welcoming Dr. Jekan Thanga. Jekan, we're going to turn it over to you.
Great, thank you. Thank you for that introduction, and thank you for inviting me to this to give this talk on a very exciting subject area, which I've been deeply involved in for many years now with my students. With this said, my talk is about advancing space exploration using multi-robot systems and swarms and the solar-powered Lunar Ark concept. With that said, our destiny is out there. We're running out of energy. We're running out of resources. We're stretching Earth's carrying capacity. And we faced several threats that can end human civilization at any time. That starts off with some of the dire challenges that we face, but there are also some great opportunities that are coming out. And really our next grand step, because we're at a pivotal time right now in which we've technologically advanced to the point that we can make that major leap. But the question is whether, of course, we have the technology to bring that all together, but also the political and moral will to do so. And so really the next grand step towards becoming a space civilization, and I would argue that there are almost like three doors to this. One is focusing on the moon. And it's nearby, it's a great shelter. Then there's Mars, of course. It's Earth-like. And then there are small bodies such as asteroids, which are resource-rich, which are plentiful, and there are many of them in close distance to Earth. And so there are all these three possible pathways, but they're all fraught with major challenges that really stretches the limit of our economy, science, technology, and human condition. And with the moon, the challenge is lack of water in significant amounts that would otherwise be needed to support a large human and living presence. The second challenge, of course, is the low gravity that we were well made aware of, thanks to the Apollo mission, but also well before that. The other is Mars. Mars is of these three destinations the most Earth-like, and of course the challenge there is it's a dry desert-like planet. Overall, it lacks resources. It's harsh. It's far away. And when I mention it lacks resources, this is again sort of comparative to Earth here. And then finally, asteroids. The challenge there is they're rich in resources and they're plentiful and diverse, But the problem there is getting access to them, and that's the very low gravity. And the very low gravity imposes a technological limitation. So given all of these factors, we argue that it is only these asteroids and comets that can be the enabler for the colonization of Moon and Mars, as they have all the required resources. But we need to get across these technical hurdles, particularly dealing with this low gravity, which serves as one of these critical obstacles. And so with advances in space exploration, we feel the focus needs to be on asteroids to really enable these other two destinations, with Moon being first and of course Mars in the longer time frame. And to explore asteroids, we really need to know their origins. The second is there are many of them. There are many in close proximity. Some of these have orbits that will eventually collide with Earth. And so this has major security implications that we need to better understand. And then, of course, as I'd said, with the rich resources, they're going to be pivotal for our space economy. And so they have major implications in all these major areas: planetary science, security, ISRU, and the space economy. And here's a view of the solar system. What you'll notice is, there's lots of little green dots. Those are asteroids in the main belt. And then these little red blobs, which are near Earth asteroids. We estimate that there are 2 million asteroids in the main belt, and nearly 20,000 have been discovered in the near Earth sphere. And this is sort of an alternate picture of the solar system, as you can see. It's large, it's dynamic, as opposed to the sort of the textbook idea of having 8 planets plus or minus Pluto. And in this environment, of these 2 million asteroids, 20,000 near-Earth objects, we have barely explored, any of them. And so that is, what is really critical into this coming future. So these small bodies hold evidence of the early formation of the solar system through accretion, collision, and bombardments. The current idea, or the current dominant theory, is that the solar system started off with about 100 Mars-sized planets and has settled on the current 8 plus Pluto. Here's an example of what could have really happened along the way. We would have had planetary scale collisions, very cataclysmic, very destructive, of course, but this would have occurred over and over again. It's all the more interesting that Earth came out of this in one piece. If anything, it got bigger from one of these original Mars-sized planets. And so the remains of these collisions are what are these asteroids that we see. And they're time capsules of these lost planets. They're composed of the early composition of the solar system, and they're diverse in composition. As I said, rocky, metallic, rubble piles, carbon-rich, and icy snowballs. As a threat, while most meteor events are benign, some pose large-scale damage to Earth, and it's happened enough that it's quite periodic. It's happening at the scale of our lifetimes. So there is major collision events that happen perhaps every 65 to 100 million years. That was, the KT extinction event that wiped out the dinosaurs. That was caused by about a 10-kilometer asteroid or a comet. That's bound to happen, under our current models and predictions. But what we're also bound to see are smaller impacts that happen at the scale of every 100 years or so. And even these are monstrous events. And we were reminded of this with the Chelyabinsk meteor impact event that you sort of see here in the video. It produced a 500 kiloton explosion. Luckily, it exploded in the atmosphere. If it had hit the ground, this would have been 50 times that of Hiroshima and Nagasaki. And in the last 30 years, of course, we've had nearly 600 meteor events of note. Most of them, 0.1 kilotons and above. So nuclear size explosions. And so given these periodic cataclysms, we can't really, sort of really discount, their threat to our civilization. And so to better understand things like impact, better understand how we can mitigate, such situations, and of course, do everything in between, which is, for example, mining for resources, moving these asteroids from one location to another. We really have to get to the science of this. And the science, of course, is getting to the early geohistory and composition. And that might, of course, involve needles in a haystack. And it's also beyond just observation of these asteroids. We've made great headway in asteroid observation. And this has been also I would say, a great achievement thanks to citizen science as well. Not just having professional scientists and astronomers observe these asteroids. We've had a network of citizen scientists who've contributed, made significant contributions to finding more and more asteroids by the year. And so all of this has been critical. But beyond just observation, we need to be able to peer underneath the asteroids. The surface of the asteroids have weathered, and often they have weathered for 4.5 billion years. And so getting underneath, we need to have ways to sort of detect how they're structured, what's inside them. And to do that, we want to do seismic analysis or radar analysis. And that would require sort of specialized missions and specialized tools and methods to really be able to do that probing. But all that will take us a step back in time to the primordial solar system. And so this has been a very exciting time for us because of the number and I would say ambitious missions that have gone ahead and have really revealed a lot more about asteroids and comets than we ever knew before. Starting off with, I would say Hayabusa 1. It went to this near Earth asteroid called Itokawa. It was a very rough and dirty mission in a sense, very low cost, a wild attempt by the Japanese Space Agency to explore this asteroid. But that really paid off for JAXA. They were able to get onto the surface. They were able to show an asteroid in such detail for the very first time. And we were able to learn about how bizarre it is, how otherworldly it is. That sort of theme came up with Rosetta. Rosetta was this European mission that went to a comet. And oftentimes we see a comet, we see its tail, how beautiful it is. But once you get to the core, we never got that far before. And with this European mission, being able to see the surface of the comet, being able to see the ice, being able to see the rapid changes in conditions, again, very otherworldly. And we're still, sort of learning a lot about that mission. And then more recently is Hayabusa 2, which is a follow-up to Hayabusa 1. And this is this has gone to the asteroid Ryugu and brought a sample back successfully to Earth. The sample is now being analyzed in the lab. And then almost like the sister mission to Hayabusa 2 has been OSIRIS-REx, the NASA-led effort to go out and do sample return from an asteroid Bennu, which is a near-Earth asteroid. It's somewhat near Earth and in an orbit that may eventually impact Earth. So it checks off several boxes in terms of what we were, sort of talking about. The other aspect about Bennu is that this asteroid is very dark and carbon rich. And that could have major implications about, how life could have been seeded here on Earth. And I'll sort of talk about that in a few minutes. So all of these missions, however, from a technical standpoint, have to perform touch and go operations over the surface of an asteroid. They couldn't linger, they couldn't do surface movement. It's because the asteroid surface is really a big unknown. And in combination, they sent out little sort of rovers or ground vehicles, you could say. This includes Mascot, Minerva, and Philae. Philae, for example, was one of the most ambitious of them all. And here, the Europeans, when they first designed these crafts, didn't quite have an idea of what a comet surface was going to look like. That's how much we were in the dark about this. And so they put in 3 kinds of instruments to have this thing land, and all 3 failed. The craft, in fact, tumbled on its way onto the surface of the comet, got some, good pictures, but it was quite a wild goose chase, being able to detect where this lander landed and what it was able to detect. Luckily, it survived for at least 15 minutes before it was able to provide data, but eventually it was lost. But what it just shows is this surface that we're talking about, whether it's asteroids or comets, totally otherworldly, totally incomprehensible to us in terms of our current understanding. And these individual crafts did their best, but oftentimes they have a very short lifetime. They get very, few pictures here and there, and they're gone. And so the challenges include asteroid mobility. The surface of an asteroid is quite bizarre. In some ways, it could feel like a liquid or a tar pond or quicksand. And that's because of the low gravity, the low escape velocity, and very low cohesion. And to sort of navigate around this, and considering how far they are from Earth, we would need autonomous control with our spacecraft. The other, of course, is the surface contact risks. That includes, this layer of dust on top, static charge, and things like porosity. Then comes other challenges such as planning, navigation, comms, and tracking, particularly because of this unknown terrain, this terrain where, it has very unknown behaviors as far as we know, and limited field of view. And then finally, to top it off, there's also the varying high and low temperature that we sort of have to face with. These asteroids, go through night and day very fast. The temperatures could drop to minus 150 to minus 200 in the cold. Shadows, of course, and it could jump up to about 100 to 150 degrees centigrade in the daytime. So these temperature extremes, also make these spacecraft vulnerable. So tackling all of these challenges, we feel you require a holistic systems engineering approach. In other words, you want to take into account the totality of all of these challenges and come out with a whole new solution for that. And our objectives here are to be systematic and follow really the systematic approach that we have been doing in the space program, ever since the beginning. And that is start off first with reconnaissance. Reconnaissance from, of course, far away from Earth's observation, to then reconnaissance up close, followed by then prolonged exploration and mobility on the surface, being able to explore the surface, being able to explore, everything unique about these asteroids and comets, and then finally, large-scale surface deployment of some kind. And this could include in situ exploration, post and pre-impact analysis. And this is further probing, particularly now looking into the interior of these asteroids, followed by things like resource prospecting, very valuable. And of course, the other is to, with asteroids that are at strategic locations, being able to use them as relays and as instruments. And so this goes all the way from science exploration to security to the space economy, and really stretches through all of them, really. So our approach is high risk, and really having to deal with this is high risk. And so that all but eliminates having to go by the conventional strategy of using one large lander or one large spacecraft to do it all. You're going to be limited by how much you could do. And so what we're proposing is use of swarms of disposable landers and crafts that can perform distributed science, and where failure is an option. And so this is sort of runs a counter to perhaps what our current space paradigms in here. And we'll sort of go through sort of why. Our model here are social insects, as humble as they could seem. In fact, these are superorganisms where it's the whole greater than the sum of the parts. They solve a complex task using many individuals, and the individuals are simple, low cost, and disposable. And here's the kicker. They've survived for 400+ million years and have withstood at least 2+ catastrophic extinction events. And as an engineered system, you really couldn't find anything else that sort of has that kind of, sort of CV of being able to withstand such cataclysms on Earth. And this is thanks to the process of evolution. Evolution that has happened millions and billions of years. And you could, in a sense, succinctly say this has occurred through a single design goal, which is survival. And through that, we have seen niche of different organisms come out. And these organisms have then, come out through complex processes of competition, selection, and innovation. And we are taking much of those same fundamental principles and applying them to engineering. In fact, there's a lot of things that we can copy towards our current engineering systems to make them better. And one of them is how to design next generation space systems and being able to exploit artificial evolutions to do that. And what's the advantage here? The potential is we could come up with creative solutions using this system that could be not thought of by the human facilitator. So it has the possibility of thinking outside of the box, literally. And so the next phase of exploration is the deployment of low-cost multi-robot and multi-spacecraft systems that explore and operate in every corner of the solar system, where they can pursue high-risk, high-reward missions here. And one of the first things that we have been implementing along this sort of vision of using swarms and multi-spacecraft systems is to come up with software tools that can help next generation mission designers to go out and really sketch out what these missions could look like. And so one of them is called the IDEA software, or the Integrated Design, Engineering, and Automation of Swarms. It's a software that's been designed by our Ph.D. students, and it's an end-to-end design tool for designing spacecraft swarm missions to small bodies. It uses evolutionary algorithms to optimize the design, and it goes into designing all aspects of a spacecraft. Spacecraft to spacecraft interactions in a swarm, to then even their trajectories. In other words, how they get from point A to point B on their space missions. And so that very much aligns with what our upcoming NASA priorities, which is, NASA has seen what swarms could potentially do, that swarms are one of these future possibilities of technology in terms of it being able to accomplish whole new kinds of science investigations and meeting high priority goals. And the other is being able to do so in new ways. One is being able to do things like multi-point measurements using a distribution of spacecraft. And that could get us, very rich data about processes that we would otherwise, not know much about. And so with this IDEA software, we come up with the software that can actually let you automate the design of a spacecraft. Then it could then automate the design of interaction between multiple spacecraft, that is the swarm. And then finally, it would automate the trajectory of the entire swarm. And so in this process, what we can do is have the software literally design our mission for us. And we are involved almost taking a back seat and giving it what are resources available, and what are the other constraints on a mission, perhaps the time to get there, the target body, and so on. So what we sort of envision is sort of this a Jetson world here, where we can take a back seat and get these automated systems to do the heavy work for us. What's also interesting about this whole approach is that it uses what is the latest and greatest out there in terms of both commercial technology and whatever other technology that's applicable for space. So what we come up with is not some theoretical spacecraft or theoretical trajectory. It tells you how we can now put it together with current technology and see it happen. And so the software is something that we're very excited about, and we're sort of really pushing ahead with various kinds of mission concepts with this approach. And we've seen some great results already. We've been applying this towards constellation design, particularly early warning systems to look out for space threats. And lo and behold, it can come up with all new kinds of different solutions, solutions that we wouldn't otherwise, sort of think of. Currently, a whole lot of different players are looking at coming up with these constellations, mega constellations, super constellations, as you hear about them, SpaceX, OneWeb, Amazon. Oftentimes they want to operate these spacecraft in low Earth orbit. Oftentimes it's to give you internet access, and to get you that coverage, you're going to have thousands of them. Okay, we could go down that route too, but we said, we're never going to be able to put out 1,000 spacecraft and manage them all. That's a gargantuan task. Can we have it operate for maybe hundreds of spacecraft? And so we can actually make that, constraint in there. We can say, our goal is hundreds of spacecraft, not thousands. Now give us a solution. And so going down that route, our system comes up with a solution of 44 spacecraft that could look and be an early warning system for meteor impacts. And it would even operate with multiple spacecraft, not in tip-top shape, in other words, facing some kind of technical issue. And it could see with a 86% efficiency. And what we also expected these spacecraft to do is have at least 2 of them watch a meteor impact at the same time. And by having at least 2, we can better position or determine their location where the impact is occurring and sort of their trajectory. So this is, in fact, an animation of that whole constellation. What you see in red are the simulated meteor impacts that are occurring, and what you see in green is the constellation. And so as we simulate these impact events, we're watching to see how well the constellation notices them and detects them from beginning to end, and does a job in being able to pinpoint where the impact happens. And so something like this would be a great advancement. While we already have capability to look for KT event causing asteroids, we don't have ones that caused Shevlinsk yet. We're still sort of at a blind spot, and so a constellation like this could really take care of that problem. Here is more of those animations. We use STK, thanks in part to AGI, and in there we have to. We don't have a separate, sort of model to represent meteor impacts, except for little missiles. So that's one of the funny, remnants that you see here in the screen. But we were able to validate this whole concept and show that we could indeed monitor these meteor impacts from the point of detection to the point of impact, which gives us some notice, which would give some advanced notice about then dealing with some of the consequences. The other is, and this is of course another open area. Despite all of the major exploration efforts we have been doing, we're still left with a few planetary moons in our neighborhood that we have not explored yet. And that includes the planetary moons of Mars, both Phobos and Deimos. And our target here is specifically Deimos, because we think is strategic. It could mean a big difference if we want to colonize Mars into the future. One of the things about Deimos is that getting to Deimos from Earth is possible with current technology, even with a manned mission. It's not too much more complex than Apollo, but we have to sort of argue that there's of course other challenges in there as well. Longer duration for that trip. The other interesting things about Deimos is it's in a resonant orbit around Mars. There are going to be some interesting mission configurations we've got to come up with. But given that Deimos is so strategic, we will almost argue that it's the gateway to Mars, particularly human gateway to Mars, that we need to know more about Deimos. At the moment, as I said, there's no dedicated mission, and we have seen Deimos only at a distance. Deimos happens to look like a potato. It's about 20 kilometers in size, and we really need detailed maps before we can send human astronauts or anything a lot more serious. And that would include, detailed parallel mapping, event observations on the surface, and of course, sun-illuminated observations. That is, observing the body at ideal, lit conditions. And so here too, we said, could we come up with a mission using swarms of satellites? And so we used ideas for this. And we said, all we can give it are 27U CubeSats, but let it figure out how many CubeSats to use. And so it comes up with this entire mission concept, going from Earth escape into heliocentric cruise, to then aerobraking around Mars, to then get into a co-orbit around Deimos, or a series of resonant co-orbits around Deimos. So it comes up with some fancy techniques to do global surface mapping, literally map the entire potato here in some sense. And this has been the focus of several of our papers. I'm gonna, very much jump over the math without speaking too much about it, but it speaks to our entire principle of coming up with this whole mission, and with this whole mission, the parameters are all an artificial genome. In other words, it's an artificial gene that's been evolved to give us this answer. So we start off with a gene that's got, random numbers, almost like junk. And you go through this whole process of artificial evolution. And lo and behold, after several hundred generations, we come up with something that's actually really sensible. And give it a few more hundred generations, it comes up with solutions that are very hard to beat, that, we have to scratch our heads and really, our experts could understand them. And so that's how much of an advantage we get. And thanks to, computation, still almost doubling every 18 months, we're only going to see it better. So with that said, we come up with this whole automated approach through a genome that solves our space mission task. And I'm going to show you in the next few slides what those solutions look like. So these are all computer generated solutions. We were hands off in terms of, how to design the craft, how the craft would encounter Deimos and so on. So Deimos, as you can see here, is in red. Is in black. And then the crafts are going in a co-orbit with Mars and Deimos, as shown before. Here's another. And so that's the resonance demonstration. So it's being able to map Deimos periodically, which is a great feat, because it was able to figure out that pattern between Deimos and Mars, which is not so straightforward. It often takes, mission designers and experts to figure that out. In our case, our tool figures it out through random trial and error over a couple of hundred generations. And here, then, you have a whole group doing it. And by having a whole group do it, you can now, instead of just taking still pictures, you can maybe even take videos. And of course, you can, map this entire body in parallel very fast. So here's how the mapping would look like. Every time it goes over, it's going to sort of show up in blue. So that's how much it is covered after all of those crafts, doing their individual mapping and compiling all that together. Right? And so as part of our efforts, we did that in simulation. That's fantastic. But we also now want to further validate the technology onto robotic hardware. And so we have our students do aspects of these validation steps in the laboratory. And so we've had a student, sort of come up with a model of Deimos out of paper mache. That's what you see here. And sort of set it up to scale. And in this case, we have a bunch of quadcopters, which are simulating spacecraft doing this flyby. And so we're taking key instances of this mission that our automated algorithm came up with, and then we're replaying it in real world with hardware to see if it all makes sense, if it all comes together. And so here's one of those simulations. And so we have these pair of crafts come in that are following what we're showing, sort of the ideal simulations. And through that, they're getting lots of glimpses of this model of Deimos. And then they're going to be able to put that together to get a 3D model of the shape of Deimos. Okay, so that's what we're really after in this case. And so the shape generated model comes out like this. In fact, it's very good. It's close to about 99% accurate. And there are little errors here and there, but that's of course after repeated runs that we've shown can actually fill for them. So given all of this, what we find is this whole process is viable. This whole process can give us new data such as event observations, videos, things like landslides on the surface of another body that we couldn't otherwise do with a single spacecraft, orbiting even periodically. So that's the neat thing about this whole swarm approach. And so we then want to extend it. And how do we extend this to exploring asteroids, moon, and Mars? And here's sort of that vision. One is we have state-of-the-art observatories now that can observe the moon and Mars with such high precedented detail. In fact, we can do it better than Earth. We have the HiRISE camera exploring Mars at the moment. And then we have the Lunar Reconnaissance Orbiter camera looking at the moon. They're giving us images of these surfaces at 1 meter plus, 1 meter or less resolution. Then, of course, we have these state-of-the-art rovers and robots going to localized areas, and they're doing a fantastic job in getting such detail about those places. But it's only those localized regions. Now, what about the rest of these planets? And so that's where we've said we got to do something to scale this up. And that's where we can send these little bots that will go out and do sort of Google Street View level of exploration. And so to do something of that scale, there needs to be autonomy, networking. It needs to be low cost, of course, but it benefits from redundancy, extensibility, dynamic reconfigurability, and I would argue the ability to improvise. And organizing such a large swarm is no easy task. Coming up with the search space for this, for a solution, we could have solutions that are 10 to the 30 million potential candidate solutions and bigger. So to give you an idea of how big that number is, that's more than our known sort of universe, where there are only 10 to the 80 atoms. And so you can sort of think about the scale here. This is a lot bigger. And that's what makes it a monstrosity of a problem. And so how do we find a solution in such a high dimensional search space? And so that's where, incredibly, we do have some great solutions. One is, of course, artificial evolution, using this whole trial and error process, which is quite systematic, stochastic, that we can actually come up with generalist solutions. But there are some trade-offs. And then, of course, using neural networks. Neural networks are a product of evolution. They're found in our advanced organisms. They have the ability to generalize, are adaptive universal approximators. And so using these two combination of tools, we've really been able to go after such high dimensionality problems. So there's also been rapid advancement with robotics and miniaturization, and with swarms. Here are kilobots from Harvard, Symbrion from the EU, some of our own excavating robots from before, and then there's Hedgehog, which is a concept out of Stanford. In our case, we have to come up with whole new and efficient ways to control the swarm. And to do that, we come up with what's called artificial neural tissues. It's a form of neural networks, but are more biologically plausible and more sort of physically connected. In fact, in this whole approach, we model the genome, in other words, the artificial genome of these systems that then produce proteins. The interaction of proteins then produces the cells and the tissue. And so we literally go towards a lot more fidelity in how it's actually done in biology. And just to give you an idea of how this works, let's just say you generate a neural network randomly. And so here are these cells all sort of randomly connected. If you were to connect sensory input, they would then somehow connect to some motor control or output and do something useful. In reality, though, if you were to randomly generate the contents of those neurons, okay, flip a dice or flip a coin or you name it, some kind of random process to generate its contents, most likely, most of those content is going to be junk. They're in fact going to have no bearing in what you're trying to do. But by random chance, a few of them are going to have the properties that you're looking for. This is almost like taking probability here, and how many random monkeys does it take to type out a perfect Shakespeare novel? It's definitely not an impossible answer here. There is some random probability that could do that, and so that's sort of the same analogy here. And so there is some very low probability that you can find the designated solutions that you're looking for, but it then becomes a difficult search process. However, if you were to let them all interact by dominance here, it's these noisy neurons that are randomly generated and that contain junk that are going to just dominate. Okay, that just goes back to second law of thermodynamics, and so they're not going to be any useful. But the key here is somehow to filter out the junk from these few nuggets in this space. And so how do we do that? And so we introduce a whole new type of neuron. In fact, we believe there's evidence for this in biology, where these neurons send out chemicals like nitric oxide and can sort of isolate and activate certain areas within their surrounding and literally turn off the rest. And so they turn on these few neurons in their surrounding and turn off the rest. And by doing so, they work in groups, and that can allow for redundancy. But these groups now are what are active. The rest of the neurons that are out there that are shown in red are all turned off. And so what we can also have is competition and even cooperation. And so a lot of interesting dynamics occur from such a very simple process. And so we code for that in software and simulations. And by encoding for this, we actually see self-organization occur in these neural tissue. And here are some of the examples applied to robotics. You can have whole teams of robots self-organize, put these blocks in a perfect lattice pattern. Here another example of robots starting off with a blank slate. So we don't have no background information. We have not programmed it. We have instead just given it a high-level goal, that is collect material and dump it in the particular dumping area and leave it be. And so after several hundred generations on the computer, that's now about an hour or so, we come up with a perfect or near perfect robot solution that we implement on robot hardware. And so they come up with all kinds of interesting behavior, how to interact with each other, how to cooperate, particularly form bucket brigades. Lots of interesting things come out of this, all self-organizing. Here's another example at the top here. We apply them even on simple Lego robots, just to show you this doesn't require high-tech, state-of-the-art robotics technology to show this as being possible. In fact, almost anybody could get involved. And so it comes up with creative behavior, not thought of by the experimenter, could be useful for scaling multi-robot solutions. In fact, we are using this approach to better understand how to scale up to these multi-agent systems. And at times, I should finally also argue, it's human competitive. In fact, it can beat humans in terms of their performance. And so we then look towards, how that innovation occurs. So we look deep down what happens, just like how a neuroscientist look at the neurons in the brain and how they interact, how they create more, how they come up with creative behaviors or innovations. We do the same, except with these artificial neurons. So a lot of understanding of the logic behind them. And then here are more examples, of course. And other things that we did was take it from the laboratory towards then applying it, in an off-world setting or in a field setting. In this case, being able to collect regoliths, being able to dig out a 3D defined surface to do landing pads, roads, and all kinds of site preparation for setting up a lunar base. And it can even do sort of mining, automated open pit mining, and do so without humans in the loop at all. And so this has been sort of our achievement over the years. And what we find is we can find optimal conditions under which these robots would operate. That is peak performance. But when there are too many, of course, there's going to be traffic congestion. But there are too few, there's not enough labor. What we can find are those optimal ratios. Even more interesting is we can find ways for them to collaborate in groups and sort of aggregate. And by doing that, they can achieve performance plateaus that wouldn't otherwise be possible in a simpler multi-agent system. And so where we could apply these are some of the most difficult exploration tasks. And that includes exploring things like pits on the moon. This was a discovery made around 2012, when there were nearly 200 of these pits detected by our colleagues at Arizona State University, Dr. Mark Robinson and his team, using the Lunar Reconnaissance Orbiter camera. These pits could be doorways to these lava tubes that have been pristine for maybe 3 to 4 billion years. And inside, the temperatures are steady, minus 25 degrees centigrade. It's got great radiation shielding, great micrometeorite shielding. It's a whole lot more sheltered than what we would find on the surface of the moon. And so we've come up with some concepts along the years of how we would go out and explore this and have them land on the surface, sending these teams of ball bots, of SpaceTREx robots, that would hop and fly into these lava tubes and go in as a team and be able to do 3D exploration of these pits. So that's one of our visions, to first explore these pits, and that really brings together smartphones, quadcopters, and how we could integrate that into a planetary environment. And so this is how they look. And so we've been doing some studies. We've been looking at how to first survey the entrances of the pit through hopping and combining these maps, then figuring out how we're going to do those jumps, and then how to then have them work in a team cooperatively to 3D map the internals of a lava tube and come up with very dense and detailed maps. And so we've also done some field tests at Government Cave in Flagstaff. And so that brings us to our sort of follow-on topic is what could these lava tubes be useful for? And our motivation here is that, going back to what we were talking about in the beginning, Earth is under threat. Humanity is under threat, particularly of mass extinction dangers. That, of course, includes supervolcanic eruptions, global nuclear war, asteroid impacts, global epidemics, climate change, global solar storms, and potentially even global droughts. And this puts us in a very fragile state. In fact, humans have already had a very close call 75,000 years ago. And so there's a need for a modern ark, we feel, that could be cost effective and that could help protect the rich diversity of Earth. It's more cost effective than creating an artificial ecosystem or a zoo to keep the species all alive. And this concept is not totally new. There's already the Svalbard seed vault in Norway, where we have nearly 1 million seeds that's critical for the world's food supply. It's a modern day global insurance policy. We want to take this a step further and store this on the surface of the not the surface of the moon, rather in the lava tubes of the moon. And why? Because it's only 4 days away. These lava tubes have been shelters, pristine in time for at least 3 to 4 billion years. And it sort of fits very well because we don't see, even given current resources, the moon becoming sort of a central location for civilization. So humans are not going to be eager to live and work on the subsurface of the moon. And so this could be a great location for that. Apart from that, we would try to save about 6.7 million species. That's about 5.1 million fungi, 0.3 million plants, 1.3 million animals. That would account for about 90% of Earth's diversity. And we've proposed that we could store it in a regional airport-sized structure that would be inside these lava tubes. And it would be held inside with a whole series of these modules, sort of assembled together inside a lava tube. It would get power from solar power at the surface, and of course communications. But otherwise, it would be sheltered underground in these lava tubes. And we would consist of a series of cryopreservation modules that would store these seeds and sperms and eggs at around -180 to -196 degrees. If we were to do this for all 6 million species here, we're looking at quite a number of rocket launches, at least 250 or so. But this is where, with current trends of the cost of launch dropping or crashing, that could one day become feasible in the next 30 years or so. The other, of course, is to have this thing modular and be able to expand and, of course, be able to preserve for a long time. And then operating at cryo temperatures is not easy. It really requires a whole new field of robotics to be advanced, which is being able to exploit things like cryo conditions, quantum levitation, and so on, which is starting to be done in the lab. And so this has gotten quite a lot of coverage, and it's really an application that brings together our thought process about using swarms, using robotics here, and really being able to take some of the areas that we've explored and applying them for the good of Earth and of course humanity. And so we've identified power and scalability of multi-robot systems and swarms. We've identified whole new ways of using them. We have said in this whole new paradigm, you don't have to have perfect robots or perfect spacecraft. You can in fact have a team of mediocre individuals that come together as a team and do some great things. And they could solve complex coordination tasks, come up with creative behaviors, cooperative mapping, coverage, etc. And really the big payoff is going to come from when we can run these things as a logistics base, mining base, and Ark large structures. But we're starting to see that. We're starting to see, for example, Amazon have an entire warehouse run by robots. In our case, we want to see these things take on tasks that humans wouldn't otherwise take on, and not necessarily go after human jobs or human quality of life here. And so what we're saying with these multi-robot systems is that they can take on tasks and scale up to areas where humanity couldn't really touch it otherwise, and of course be able to exploit them for their high efficiency, creativity, continuous operations, and rapid reorganization, particularly to allow us to work in these extreme environments that are otherwise not conducive to humans. And so with that said, I wanted to acknowledge my current and former students who've been involved in all of this work. And here is the whole list of them from several institutions and some of my collaborators in this work as well. And with that, thank you. and I'll be happy to take your questions.
Well, thank you so very much, Dr. Thanga. That's a fascinating, it's a fascinating topic, and it's a great talk. If you have questions for Dr. Thanga, you want to go ahead and type those in the chat. I don't think we have any yet, so we'll wait a couple minutes to see if anybody's got any questions for you. Okay. You mentioned improved resolution by overlapping fields. Have you looked at retinal photoreceptors and how they act to accentuate contrast in a similar fashion?
That's a great question. In fact, the whole idea of that principle of overlapping fields being able to produce a better resolution than what they start off with, came from models of the retinal field, and so it comes back to the same source. That was, one of the I would say inspirations for coarse coding, as it's called. It's been sort of taken from neuroscience and particularly neuro-optics, and it's now been adopted into computer science. But that's where the principle sort of comes from. In our case, we've said with this whole coarse coding principle, it's so generic and it's got such wide applicability that what we also noticed was another gentleman noticed that it is a basis for operation in the cerebellum. The cerebellum being the part of our brain that does fine position sort of muscle control, and so not just in the optics, but in muscular control, and so two different places. And so we said, it's got to be more generic than that, and so came up with this whole theory that it plays a principle or plays a part in literally coming together and organization of single and multiple neurons in being able to sort of throttle their signal, throttle their capability in turning on networks of neurons and really that allowing for some form of self-organization. And as wild as that may start off to look, from our simulations, we see all kinds of interesting attributes come out from this sort of self-organization principle. And really, we're only scratching the surface of this. There's still a lot more to do.
I think that's our only question, and we are out of time. So we're going to conclude our program this evening. And again, thank you very much, Dr. Thanga, for joining us tonight. We really appreciate it. It's a great talk and fascinating topic. And
great. Thank you. Thank you again.
Yeah. So I'm going to go ahead and end our session. Thanks, everyone, for joining us tonight.